Okay, hello everyone. Well done for braving the weather today. So today we're going to continue on the probabilities part of this course. Last week I started introducing, that was pretty much a theory-heavy course. Last week I started introducing lots of definitions so that we knew what we're talking about. But in a sense, I didn't really touch on any more practical problem there. You know, this was only definitions, but it may have been unclear how this is really useful in practice and what type of problem we can solve with that. We're going to touch on that today. So effectively, the point of today's lecture is going to be to use the definition we've seen last week in order to look at what can we do with those definitions when we have a problem that combines a number of random variables together. And how can we effectively use those definitions to manipulate the amount of information we have on them. So that means that we're going to look at, so when we have multiple random variables, at joint distributions, conditional distributions, what's called marginalization, and also, and importantly, one of the key points today is to discuss Bayes' rules, which is the most fundamental tool that you're going to use in order to manipulate probabilities and reason using probabilities. So that is the plan for today. So basically today's learning outcome, understanding what we mean by conditional, marginal, and joint distribution, what entropy is and how it can be computed, then Bayes' rules and how to apply it to problems, and also, incidentally, what diagrams are and how they can be used. Okay, although this is more of a detail of the application we're going to use today and a bit less fundamental to this course. So for that, I'm going to go back to the example that we took last week, which is, if you remember from last week, we looked at a number of texts, and in particular, we looked at Romeo and Juliet, okay, from Shakespeare. And what we did is that we looked at all of the letters that were present in this work, in this book, and we calculated a probability distribution using the empirical distribution of how likely a letter was to appear in this text, according to how frequently it appeared. Okay? And if you remember, what we did also is that then we did the same thing for another book from a different author, which was A Transformation from Franz Kafka. And we ended up with a very similar distribution, slightly different, but still very similar distribution. Why? Because the distributions of letters, the frequency of letters in English text is mostly driven by the language you're writing in English. If you were looking at a text in a different language, you would see much more difference. Nonetheless, what we could see last week is that just using this very simple model and those two distributions that are very similar, if we took two other texts from the same authors, so which one was it? I think there was Hamlet from Shakespeare and The Trial from Kafka were the two other texts we took. Then when we were effectively looking at all of the letters in those two new books and calculating how likely it was that those books would be generated by the distribution we calculated from Romeo and Juliet and The Trial, we could find that effectively Hamlet was more likely to have been generated by the distribution of Romeo and Juliet, and The Trial was more likely to have been produced by the distribution of The Transformation. Okay? So that shows that even with very rough models, we can already use that in order to obtain information that is not completely trivial, in this case, of two different texts. So we're going to go back to that, but try to do a little bit better. So we go back to this idea. So we have a text that is in this case Romeo and Juliet, and last week what we did is effectively we modeled that by taking all of the letters, putting them to lowercase, and we ended up with a distribution that was like that. So that's what we've done last week. Then we took the metamorphosis and did the same thing. So again, those two distributions are very similar. Just want to switch from one to the other, but not exactly the same. Okay. Now, from this PMF, we can draw samples. That's another thing we did already last week. If you do this, you end up with something like this, which is just a chain of letters that do not effectively give you anything meaningful. Why? Because there's not enough information in just a distribution of the frequency of letters. Okay. So in a sense, you have this picture in this slide of a monkey on a typewriter because of the infinite monkey theorem. I don't know if you've encountered that already. If you've not, then look it up afterwards. This is effectively a thought experiment that is about reasoning about infinity. That was the idea about this thought experiment. And very often it's used wrongly nowadays, because this is really just about reasoning about infinity, not to draw any other conclusion. But the idea of this thought experiment is that if there is a limited number of letters that you can put and a limited number of ways that you can arrange them, then if you had a monkey typing randomly on a typewriter, and this monkey had an infinite amount of time typing on this typewriter, then at some point he would type all of the works of Shakespeare amongst all of the other stuff he would type, okay? Just because there is a limited set of things you could write, and if you have an infinite number of time, random search will give you at some point any possible thing. Now, why it is wrongly used, and that's worth saying at this stage, is because, well, obviously, if you have a monkey and a typewriter, the monkey is most likely just to maybe type twice on the typewriter and start kicking it and stop interacting with it, okay? Even if you assume that the monkey is going to type on the typewriter, he's likely to keep on typing the same patterns again and again and again. So it's very unlikely that a monkey in practice would really just go and do a proper random search. But also, those are details. Even if you assume the fact that the monkey is a metaphor for effectively having a process that searches randomly, the important thing in this thought experiment is that it's about reasoning about infinity. This is true if you have an infinite amount of time. And there's a lot of mathematical proof that will tell you that given an infinite amount of time or an infinite amount of resources, this algorithm or that algorithm is guaranteed to converge. But obviously, in the real world, we do not have an infinite amount of time. And if you actually do the calculations that underlie this process of typing random letters, if you just were to sample random letters and try to create text, it would actually take you more than several times more times the life of the universe in order to be able to generate even a page of the works of Shakespeare, okay? So the bottom line is, it's important to know that this is a very interesting theorem, but the only thing that is supposed to show you is that if you have infinity on something, everything is possible. When you don't, like in the real world, this does not apply, okay? So that's a bit of an aside, but I think this is not completely unrelated to the kind of problems we're looking at right now in this course. So basically, to go back to what we had effectively a probability distribution function that we calculated using the empirical distribution by effectively measuring the number of times that a letter was occurring and dividing that by the total number of letters. So that's a way to obtain that. Now, when we have that, we could calculate the likelihood function of any given text, and this likelihood function gives you an idea of how likely is this text to have been produced by a random process driven by the probability distribution that we had, okay? And we'll come back to this type of formulation again and again. And so basically what you can do is, assuming that each letter is independent, this is effectively just the product of the probability of each of those letters, okay? And then if you calculate this long product, you end up with a number that tells you effectively how likely is the text to have been generated by this. So this goes back to, and this brings us back to an important thing that we discussed last week, which is that when you start doing this type of thing, it's usually absolutely critical that you start using logarithm of probabilities rather than actual probabilities, because although it works in maths when you write it down yourself to say that you take the product of all of those probabilities, if you actually on a computer try to multiply 1,000 or 10,000 probabilities that are all below 1 together, you're going to end up with 0. Okay? You're never going to end up with anything important. On the other end, if you take the logarithm of those probabilities and take the sum of that, because the logarithm of a product is a sum of logarithms, by the definition of the logarithm, if you do this, then you end up with an actual value that you can actually use and that is really quite reliable. So in this case, you can end up with a number that is, in this case, minus 344,778 and something. The point is that this log likelihood that we have here in itself is not interpretable necessarily, but what we can do with them is compare them, okay? And this is exactly what we did afterwards, is effectively looking at the probability mass function that we had for two texts, Romeo and Juliet and Metamorphosis, and when we had a third text, calculating for this third text what is the likelihood according to those two separate distributions, and then we can compare those two numbers, okay? And that, on the other end, is easily meaningful. If one is larger than the other, it means it's more likely. So this is basically what we did last week. I just wanted to remind you a little bit of that, because what we're going to do at the start of this lecture is go back to this problem, but try to do better. Okay. The first thing and the main limitation we had in what we did last week is just that modeling a text according to individual letters is really a bit weak. Okay. Obviously, individual letters don't tell you much about a text. Now, obviously, it would be much better to do that according to words or to fragment of words, which is the way language models work nowadays. But without going necessarily to all this complexity right now, we can really already try to make things a little bit more sophisticated by looking at bigrams. And so the idea of bigrams is just saying we're just going to do a little bit better than last time. Instead of looking at individual letters, we're going to look at pairs of letters, okay, that are following each other. So, for example, we can take every pair of characters in the order that they appear. So effectively, the character in green here, CI, and the character just before that, CI minus 1. And we do that for every position in the text, okay? So that means that we now consider two characters, and that means that effectively those two characters will have different probabilities, right? So this is what's called a bigram model, okay? And there are more than that. There are unigram, where you have only one value, that's what we did before, bigrams, where you have two values, trigram, where you have three, or n-gram models, where you have effectively n number of items that you're considering. So that's a fairly generic ID. So really, gram here refers to a unit. So it can be a character, it can be a word. You can do the same thing with words, where you'd look at pairs of words. Just going to stick to characters, because then we simplify things and we don't have a vocabulary that is too large. So effectively, what we're discussing here is a character bigram model. But again, that could be everything we're going to do here could work with any other bigram. So, if we have a bigram, then what we're looking at really is what is the probability of two characters happening together one after the other. Okay? So that's a joint probability. So that's the probability that random variable x and y are happening together. That the character c at I minus 1, at position I minus 1, and the character c at I are happening together in the text. Okay. Basically, this joint probability tells us that those two things are happening simultaneously. So another way of writing it, that we're not going to do again because it's quite heavy in terms of writing, is saying there's a likelihood that this character happens, that x happens, and at the same time that y happens too. Okay, so that's effectively an intersection. Now, when we have joint probabilities like that, one really important operation that we can do is marginalization. So that's a word that you'll find a lot when you look at probabilistic texts or any application that use probabilities. Marginalization is really the derivation of the probability of x from the joint probability p of xy. And effectively, you do this by just integrating all the joint probability over all the possible outcomes of y, okay? So in practice, what it means is that the probability of x can be obtained by taking the integral over all values of y of the probability, of the joint probability of x and y, okay? And that is the case for a continuous distribution. And as we've seen before, as ever, in the case of a discrete distribution, we can replace this integral by a sum, and we have that the probability of x is equal to the sum over all values of y of the probability, of the joint probability of x and y. Okay? Now this is extremely useful because that means that it allows us to compute a distribution of one random variable from a joint distribution. Okay. Now obviously here we are just introduced a joint distribution, so it seems a bit artificial. But the thing to keep in mind here is that this very simple example we have here, that holds also for the case where we have 2, 3, 100 random variables. Okay? And in practice, what we'll find is that when you have many random variables, it may be easier to effectively estimate the joint probability from the data you have than the individual probabilities. So marginalization is something that you'll have to do often in order to extract from those joint probabilities the individual ones. So really what that means, marginalization, is just this idea that you're just going to integrate over one or more variables from a joint distribution. And the effect of that is that it removes those variables from the distribution. Now what we can say is that two random variables are independent if they do not have any dependence on each other. It's an obvious statement, but that's the case when the joint distribution is just a product of the individual distribution. So that's the assumption that we made before when we were looking at the whole text. When we calculated the likelihood over the whole text, we just took effectively the product of the individual probabilities of each of the characters. Okay? So that means that they are independent, or that you assume them to be independent. The important thing is that it's not true in general. So in the general case, most variables in most real problems will have some sort of dependence. Now the other notion when you have more than one variable, when you have multiple variables, is that if you have joint probabilities, you can also have conditional probabilities. So conditional probabilities is effectively what is the probability of a random variable x given a random variable y. And that's written as p of x, the vertical bar, that means given, and y. Okay, so that means what is the probability of x given y. So effectively, if you know that y has already happened, if you know that in your text you already have a certain letter, let's say the letter q, what is the probability of the letter that immediately follow? Okay? So in this case, obviously the letter u has not necessarily a very high likelihood in any text in English language, but if you already know that the letter q, which is very rare, as happened just before, then this conditional probability is very high. So that's a case where the joint probability would be low of qu, but the conditional probability of u given q is high. Okay? Now, intuitively, what that means is that this conditional probability is written like that. It's effectively the joint probability of x and y happening together, so the fact that the two things happened, divided by the probability of y. So what does that give you in practice? That means that, well, intuitively, when you look at this, if the probability of y is very small, that means the conditional probability is going to be higher as the probability of y decreases, as the probability of the event you know has already happened decreases, the conditional probability increases. Conversely, as the probability of y tend to increase, the conditional probability would decrease. Why is that? Because again, if we think of that in a diagrammatic way, okay, and let's say that you have a situation, you have a set of events that are all of the states of the world where y is true, and they're here. And now let's say that you are looking at the probability of x, knowing that y has already happened. Well, the first thing you can see is that if all of the cases where x happens are the cases where y happens already, that means that if you know y has happened already, you know that x has necessarily happened. The probability is going to be 1. Okay? On the other hand, if you're in a situation where x is here and the subset where y happens is small, then when you have y that has happened, there is a lot of possible states where y has happened but x hasn't happened. So that means that your probability of x given y remain low. Okay? So that's the intuitive explanation behind this formulation. Now in practice, what is good is that it gives you a way of going from joint distribution, which as we'll see is usually easy to calculate in practice or to measure in practice, to conditional distribution, which may be harder to measure, but is useful for making decisions. So this is another illustration of this visually, okay? So if we look at this here, and you try to look at this diagram, what would be the probability P of x? Well, that would be effectively the blue circle there. The joint probability P of xy would be given by the area in green, that is the intersection between the yellow and blue circle, divided by the total area of the square of all possible outcome. And the probability of x or y would be effectively the probability of x plus the probability of y minus the intersection in order not to double count it. And if you wanted to marginalize then the probability of xy over y, you effectively just need to integrate all that over all possible value of y, so true or false. Okay. So let's go back to another example that's a little bit more practical, that's related to what you do in the labs, which is the case of the scorpion. So again, let's assume that you got a grid of outcomes, that's 6 rows and 8 columns, so that's 48 possible grid cells where the submarine can be. Okay. So then we can define an event that could be the event solve that covers all of the cells for which the first coordinate is 4 or more. So effectively that's all the yellow ones here. Then we can define an event east that we're going to call east, the event y, that is true if the second coordinate is 6 or more. So that's all the red one there. Okay. So again, if we try and look at this diagram, we can try and calculate now what is the probability of x being true. So you need to calculate effectively all of the grid cells for which it is true versus all of the outcomes in grid cells for which it's false. So you can see this is exactly half in this case. So that means the probability that x is true is 0.5 according to this diagram. So probability that y equal true on the other end is going to be 3 divided by 8 in this case, because there are 3 columns for which it's true out of all possible 8 columns. Okay. What is the probability that both x is true and y is true? So again, you have a 3 by 3 region and both of those events are true. So that's 9 outcomes out of the total 48 outcomes. It's 9 out of 48. Okay. So all of those things are really quite easy to calculate effectively, just by hand, looking at this simple case. Right. So there I've put those calculations so you can look at them a little bit afterwards, in addition, as a confirmation of whether you've understood all of those things correctly. So back to diagrams, okay? So now that we've defined those little things, we can go back to our text and we can say from the vector of character codes that make up, for example, the metamorphosis, we can take every pair of character in the order that they appear, okay? The joint distribution of bigrams is given by the normalized count of each character pair. So for each position, you take the 2 characters, and effectively now you're going to create a bin for each possible pair of characters. And so if you have 26 letters, it's 26 times 26 possible bins. And every time they occur, you add 1, and then you normalize that by the total number of pair of characters that are present in the text. Okay. So same process as before, really. Once you've done that, you're going to have effectively your empirical distribution for this joint distribution. So then what you can do is you can calculate the marginal distribution P of Ci, for example, from this joint distribution by really summing over every possible character C of I minus 1 And likewise, you can marginalize for C of I minus 1 by marginalizing over the following character. Once you've done that, you can then also calculate the conditional distribution by taking the joint distribution and dividing by the count of, so if you want to have the probability of the second character given the first character has already occurred, you take your joint distribution and divide it by the probability of the first character that has already occurred and that you've observed. And so it tells you the useful thing that what is the likelihood to observe a specific character given that you've already observed another one character just beforehand. So basically, this is quite easy to code in Python. What you can do is really you join probability because you have two variables. You're going to model it typically as an array, as a matrix, as a grid if you want, where you have one variable that corresponds, the outcomes for one variable that correspond to rows, and the outcome for the other variable that correspond to columns. Okay? And so for every pair of letters you have, that correspond to one value in your matrix or in your array. So once you've done that, you can effectively just go through all of the character pairs in your text. So we do that in Python by just effectively taking one version of the text, shifting by what character, zipping the two texts together, and taking every pair of character at every point. So that's just a clever way of doing this. And effectively, for each of those positions, you just increment the position in your matrix. And then you can divide at the end by the total number of elements you've added. So it's really straightforward code to write. What is the output of that? Well, we can visualize now this probability because, so it's an histogram, but a two-dimensional histogram. So we could visualize that in fancy 3D, but that's usually awkward to look at that. What's better to look at this often is to look at them from the top by saying that we're going to associate a different color depending on how high each of the bin is. So in this case, we have the case where if we have a probability of 0 for the two characters, we have something that's very dark blue. And as the probability increases, it goes towards yellow. Okay. So in this case, what do we have? We have effectively the first letter being in rows. So that's here. And the second letter being in columns there. And what we can see just by looking at this is that there are some combination of letters that seem to be more likely in the text, as we would expect. For example, here we have that T followed by H is very common in the English language. I'm sure you will all have noticed that. Another thing that is quite common is H followed by he. And then what do we have? We have E followed by R in this case. Okay, so those are effectively the case where you have combination of two letters that are particularly common in the language. Okay, so that's a bit nicer. It gives you a bit more of, it models a little bit more the pattern of letters that you have in the language. And from this, then, we can simply try to do the marginalization as we said before. It's a really straightforward thing. You just need to calculate the sum of this joint distribution. And depending on whether you want to marginalize for Ci or Ci minus 1, you do this sum over one axis, over rows, or over columns. Okay, but in any case, it's extremely simple to do. So if we do this, we end up now again with having a distribution for each character that is going to be very similar to the probability that we calculated before when you looked at unigram instead of bigrams. Okay. So not much necessarily to see there. But obviously the point of marginalization in this case is that it gives us a way to calculate this conditional probability, because we already have the joint one. If we have also the marginalized probability, we can then calculate this ratio. So again, there is nothing particularly tricky there. If you look at the code, we're doing exactly what's in the equation there. And then we obtain a new matrix that is a conditional probability now of what is a letter given what the previous one was. But the patterns here that we see are quite different from as what we had for the joint one. And obviously the prevalent thing that we would have expected here is that if you had the previous letter that was a Q, then you have the following letter is extremely likely to be a U with a probability of nearly 1 in this case, okay? That's a much higher probability than anything we've seen before. Again, as a way to check, if we go back to the joint probability we had, there was really not that much probability for Q and U, because in any case, this is not such a frequent combination of characters. So that shows you really the strong difference between those two concepts. So this is a very useful thing, because often when we talk about decision, making use of those probabilities, that's really the conditional probabilities we're interested in. What is the likelihood that something is true given the stuff I've observed? Okay, that's the type of question we want to ask. So here's an aside. So I talked a lot about how, we're using a very simplified model here, where effectively we're only using individual characters. And now we went to bigram, and I said that you could effectively try to get that, make that a little bit more interesting by using words. And I think it's worth mentioning that it's not so different from what is done by large language models in practice, although it's outside of the scope of this course. It's interesting to look a little bit at how they work. So this strategy is really similar to what those do. So for example, GPT and all of those large language models effectively have a process in which they generate one word at a time. Not exactly words. Effectively, they generate fragments of words, but that comes pretty much to the same. So basically, they generate one word at a time, and they do that by sampling from the distribution of the word what is the likelihood of the next word given all of the words that came before. Okay, so it's effectively a very big conditional probability that's being used, and you sample from this conditional probability that gives you a word. This is including the user query, the question you asked, and the words that have been generated by the GPT itself before. Okay, so that's what's called an autoregressive model. Okay, and all of those approaches are effectively autoregressive like that. So, for example, if you have already a sentence that starts by once upon, you'd process that, you'd send that into an LLM. You could have an output for the next one. It could be A. And then you take once upon A, you add A at the end, and you put that again through the LLM, and it's going to generate time, for example. And if you add that at the end and put that into the LLM, the next word is generated, and so on and so forth. Okay. So, and this is a more realistic example where we have effectively a conversation between a human and a bot. And effectively, you have what was the previous steps of the conversation, questions and answers, that are put as an input to the LLM. And then this LLM effectively use this word-by-word autoregressive sampling to produce an answer that is then provided to the user. And when the user answers again, the previous answer is tagged on top of the input of the LLM. The new question or response of the user is added again, and the same process is generating word by word the next answer of the LLM. Okay. So this is how those autoregressive processes work. But that gives you an idea that this notion of conditional probabilities scales up really, really well to very large models and very large problems. So, what I suggest is we're going to take a slightly early break here. I usually take it a little bit later, but I want to get then onto Bayes' theorem, and I think that's better if you're fresh for that. So let's take a 10 minutes break now, okay? And at 10 to reconvene, and we'll start talking about Bayes' theorem, okay? Good.
Hello, yeah.
Sorry, I came in late, so I might have missed a bit in the beginning. But is the joint probability essentially the intersection?
Yeah, yes, that's it.
Okay.
That's the intersection of the two.
So why bother having a fancy term for that? I got confused in the beginning.
Um, because the intersection is an operation that
But
you
the
can do
joint
between two
probability
sets.
is a
It's a
distribution.
distribution.
Right, right.
And the thing always to keep in mind is that when I'm presenting here, I'm presenting it for a simple case, minimal case of two variables.
Okay, right, right. But actually the
In
cases are
practice, you're
larger.
talking about hundreds of
And
variables, and
so intersection, it's like x comma y. Is that the same as y comma x, right?
yes.
Okay.
So the order is not meaningful for the joint probability,
But it is for
but
the
it is for the
conditional,
conditional.
right? Right.
Okay, so I mean, I know that those things, when you look at that for very simple case, they look very trivial,
Right.
but then you will see some derivation, in text where some proofs are made, and the way the variables are shifted around in joint
Right.
probabilities can be a little bit
Because like
surprising.
even in this case, Q, then you, it makes sense like quiet and
Mhm.
some other words, but U and Q would never happen,
Exactly,
right?
it cannot happen. So that's why if you look um, at the difference between the joint and the conditional, one is much more asymmetrical than the other. Okay, um, it's not necessarily completely symmetrical because obviously there was a slight offset in the text, so there might be a in the way we estimated the probability, there is still so
The
yeah.
correlation.
So yes, the, the thing to keep in mind is that when you have a joint probability of two random variable, you can move them around, right?
Right.
But the meaning of each variable is not necessarily interchangeable. So what I mean by that is, in the case I've showed, you have no, I'm off. Okay, good. You have two variables, x and y, that correspond to the first letter and the second letter.
Right.
Okay.
So the
But if you move them around, you still have that y. If you have p of y comma x instead of p of x comma y is still the second letter and x is still the first letter. Okay.
oh wait.
So you see what I
So
mean?
we've already assigned meaning to what x and y
Yeah.
mean in this case. So the value might be the same, but that doesn't mean that if we reverse the order, the
You can
probability
reverse
would be
the
the
order,
same.
but that
Right.
doesn't mean that it's the same
Right.
thing. So it can
Okay.
be confusing sometimes
Okay, got it.
because of
Because
that.
I was thinking about that specifically too, like the order. Because I mean, it's kind of obvious because
Mm-hmm.
we're dealing with letters,
Yeah.
right? And the probabilities won't be the same
No,
depending on the
that's it. Because what I
letters.
was saying was wrong. It's obviously for the joint probability is not symmetrical
Right,
because
right.
the two variables
In,
are not
but if you think
interchangeable. You
about it
can
in
move them around.
intersection term, if it's in a Venn diagram, the value is the same.
Yeah, yeah.
Like no
The
matter
value is
if
the
x is
same,
this side and
but
y
the
is
two
this side.
bubbles are not the same again in terms of Venn diagram.
Thank you. I understand.
Yeah.
Do we have a MOOC exam this year?
Sorry?
Do we have a MOOC exam this year? The MOOC exam.
A mock exam.
Yes.
I don't know if there's going to be a mock exam. So this is mock exams are done by the school for the program. So you need to ask the program lead for that.
Okay.
We will do a revision session before the exam.
Review session is based on the previous past papers, or
Yeah, yeah.
thanks.
So okay.
Okay, let's start again now. So now that we've seen and we've introduced how to deal with joint probabilities and with a case over multiple variables, we're going to look at Bayes rules and Bayes theorem, which is the key tool that you're going to use in order to reason and to combine them. What we have right now is joint probabilities. We know to measure them. And we have conditional probabilities that we can calculate from a joint probability distribution by using marginalization. Okay, so we have all of those tools yet. So I'm going to start with an example again, but a different one, less literary one, and something that we experienced a few years back, which is the case of, let's say that you have a pandemic. Let's call it Plague X, okay? And let's say that there is this pandemic that's going on, this really nasty disease, and that a group of scientists have developed a new test that can detect Plague X with a 95% accuracy. Okay, so pretty good test. Now, we'll assume that this 95% accuracy means a 5% positive rate. So that means that 5% of the time, people who don't have the disease will test positive nonetheless. Okay? We also mean that it means 5% false negative rate, so that means that 5% of the time people have the disease but will test negative. Okay? In practice, in real cases, those two false positive rate and false negative rates are different. So when you talk about accuracy, that's a combination of the two. But in order to simplify a little example here, we're going to assume they're exactly the same. Now, let's say that we also know that there is one person in 100,000 that are known to have this Plague X. Okay, so that's the prevalence of this disease in the population. Okay? And how do we know that? Well, there might be several ways. We can know that because, well, for example, let's say it's universally fatal. You always die within 1 year. So that means that effectively we know that afterwards by counting the bodies. But there may be other ways of estimating that are less dramatic. So one way is that there may be some, for example, during the COVID pandemic, there were people who were trying to estimate the prevalence of the virus in terms of hospitalization, but also in terms of, for example, presence of the virus in wastewaters and things like that. So there may be other ways to estimate this prevalence. Let's just assume that we have this figure. Now, you go for the test, and as you get your test, there is a second bar that lights up, so you test positive for Plague X. Question: how likely are you to have Plague X? Okay. So I decided to put a little bit of a test here. I'm not going to ask you to raise your hand this time, but there is a QR code. You can go on Mentimeter, and you can vote for that. Okay, you got a number of options. So let's try and do this and see where that leads us. Okay, everybody voted? All good? You'll see, I mean, in Mentimeter there's a few options, so you don't need to make precise calculations at this stage. Okay, it's all good. So I'm not going to give you the answer now. But the point is, I want you to keep in mind this scenario, because when we're going to explain Bayes' rules, that's typically for this type of problem that it's useful and why it's absolutely necessary. So what is Bayes' rules? From a very practical perspective, we often know the probability of some event A given some other event B. Okay, that would be the probability of A given B. Okay. So often we want that, so that's what we want to have. So for example, the probability of having the plague if the test was positive. But often we're in a situation where we can only compute the probability of B given A. So for example, the probability of the test being positive if we actually have the plague. Okay. So those are, so this is a very frequent case where there is one conditional probability that is available, easy to calculate or measure, but that's the other one we want. The point about Bayes' rules, in practice, in very practical term, is that it allows you to turn that around. It allows you to calculate P of A given B if you already have P of B given A. Okay. So usually the practical case we're going to have is that we know how we have, for example, a mysterious entity that behaves that gives you B given a certain number of variables A. We know the data that we saw, P of B, so that's the thing we've observed, and we know what the mysterious entity is likely to be up to in general, so that's P of A, okay? And from those things, we want to work out what the mysterious entity is doing, P of A given B. And that's what Bayes' rules does for us. Now, the first bad news is that in general, really most of the time, P of A given B is not equal to P of B given A. The two things are not the same thing, virtually never, okay? And the two expressions, in addition to that, can be completely different. Now, typically, these type of problems, when do that occur? When you want to know the probability of some event given some evidence. You've measured some evidence, and you want to know how likely something is. So how likely is that I have a disease given that my blood test came back positive? So if we think of this, the evidence we have, the fact that the blood test turned back positive, is something that is caused by the thing we're interested in. Okay? The test is likely to be positive because you're infected or not, so that's what's causing it. Okay? But what we know is only the probability of observing the evidence given the event. So we know the causal relation, basically. So if you have this disease, the blood test will come back positive 95% of the time in this case. So Bayes' rules gives us the mathematically, theoretically, and absolutely 100% correct way of inverting this probability distribution. And that's why this is such a useful rule. Basically, it gives us the relation that the probability of A given B is equal to the probability of B given A, okay, so the evidence that we have, multiplied by the probability of A, so how likely was A to occur to start with, divided by the probability of B. So that follows directly from the axioms of probability. If you look at the axioms that I gave you last week, the definition of conditional probability and joint probability, you will see that you could prove this actually quite easily. So this is not miles away from what we've seen. But despite it being so simple in appearance, this is an extremely useful formula. And it has really some surprising consequences often. Now, in terms of nomenclature, P of A given B is called the posterior probability. That's what we want to know. Okay? The posterior is what we're interested in. That's a result of our calculations. P of B given A is sometimes called the likelihood. So how likely is the event A to produce the evidence that we see? So the evidence that we see is B. P of A is what we call the prior. So before we've seen the evidence, or regardless of this evidence, what was our belief that A had happened before? Okay? So it's really the very Bayesian thing that we had a prior belief that A is true. We collected some evidence, we calculate a new belief that A is true after, posterior belief after having this evidence. And P of B is the evidence. So how likely is this evidence to happen regardless of the event? If something is very likely to happen, it's basically not very informative, right? It's not surprising. You know, think of that, you can think of that as being a crime story. Everything that is very likely to happen is not an evidence. But something that is very rare or unusual on the other end will be some sort of evidence. It will give you some knowledge that may allow to update your posterior. So basically, another way to phrase this is to phrase this as saying that there is an hypothesis H that we want to know, given some data D that we observe. And then we write your Bayes rule in the same way, just replacing the variables by saying the probability of the hypothesis given the data is equal to the probability of observing this data if the hypothesis were true, multiplied with the prior belief that the hypothesis is true, is it a plausible one or not, divided by how likely in general it is likely to observe this data. Okay? So that gives you, again, a bit of information about this ratio. If it is the case that this probability, that the evidence you've observed is very likely, then it doesn't give you a very high conditional probability because it's not updated your posterior that much. Okay? On the other end, if it's a very rare event, then you're more likely to have a posterior that is much more informative than your prior. Right. So once you have this, another part of Bayes' rules that is kind of essential is that you need to bring in marginalization in order to apply it in practice. Okay? So we can see that the posterior probability is proportional to the product of the prior and the likelihood. But to evaluate its value, what we need is to compute P of D, the evidence. So how likely it is to observe this data. Now, that is a quantity that in many practical problems is actually quite difficult to estimate. Okay? So in practice, the way this is calculated is by marginalizing this probability of this data from the joint distribution of H and D, of the hypothesis and the data. Okay, so that means integrating this joint probability over every possible outcome, every possible value of your hypothesis. Okay. So basically what it means is that you can write this P of D that is often inconvenient to calculate as being the probability of D is equal to the sum of the probability of D given that the hypothesis is true, multiplied by the probability that the hypothesis is true, plus the probability of D given that the hypothesis is false, multiplied by the probability that the hypothesis is false. And that usually is something that you do have because we assume again that this probability of the hypothesis, we know that, and that the conditional probability of the data given the hypothesis, we also have that. So that's an important trick because that means that out of those three quantities you need to apply Bayes' rules, you actually only need two, and you just need to use marginalization in addition. So basically this is what you end up with. So that means that the probability that the hypothesis is true is equal to the probability of the data given that the hypothesis is true, multiplied by the prior probability that the hypothesis is true, divided by the sum between the probability of the data given that the hypothesis is true, multiplied by the prior probability that it's true, plus the probability of observing this data if the hypothesis actually were false, multiplied by the probability that this hypothesis is false. So that's the general form of Bayes' rules, except that obviously if you have more than one possible outcomes, this sum becomes bigger. And if you have a continuous, the case of a continuous variable, you would have an integral instead of a sum. So what it means that if we go back to plague X, we can effectively try to take these Bayes rules and apply it to plague X by saying that the probability of the plague given that the test result was positive is equal to the probability of getting a positive test if we have the plague multiplied to the prior likelihood probability of having the plague multiplied by the probability of having a positive test. We don't know what is the probability of having a positive test, but what we do know is what is the probability of having a positive test if you have the plague, and what is the probability of having a positive test if we don't have the plague, because that's in part of those false positive and false negative rates. So we can effectively obtain then this P of test by summing, effectively marginalizing the probability of the test over all of the possible situations being infected or not. We can effectively, once we've done that, we can write that pretty much as it is in a Python code, plug in the numbers that we had. So we have effectively the prior probability of having the plague is 1 in 10,000. So that's what we have here. Then if we have the plague, the test is positive with 5% error. So that gives us that the probability of having a positive test if we have the plague is 1 minus the error, so 1 minus 0.005. If we don't have the plague, we say the test is positive 5% of the time. So that means the probability of a positive test if we don't have the plague is 0.05, so 5%. So far, so good. Then the chance that you don't have the plague before we see the test is effectively 1 minus the chance of having the plague, because again, there's 2 possible outcomes, so they must sum up to 1. Once we've done that, we can then finally integrate over the evidence to get the probability of getting a positive test. We multiply the probability of the test given when we have the plague by the probability of having the plague, and the probability of the test if we don't have the plague by the probability of not having the plague. That gives us this. And then we can just plug all of those numbers into Bayes rules, and that gives us the probability of the plague given that we have a positive test. And if we calculate that, we can see that we have effectively 1 chance in 5,000 or something like that to actually have the plague. 1 chance in 5,000. Wow. So if we go back to the initial story, here are the poll results, by the way. So, not bad, not bad, not bad. But basically, if we go back to that, that makes you think a little bit. When I gave you the problem, you know, the idea that you have a test that's 95% accurate, it's pretty good. It's not a bad test, okay? But then even when you have a positive test, you're still vastly more likely not to actually have the plague. So how useful is this test? Well, this is why Bayes reasoning and Bayes rule is so useful for even for very practical things, just because there are counterintuitive things that if the prior likelihood of an event is very rare, even a fairly strong evidence like a 95% chance test still make it less likely that this event happens. Okay? And that's something that is very counterintuitive and that you only really see when you plug the numbers into Bayes rules. And this is something that is extremely prevalent in many cases. So there is, you can see that, for example, for when you do screening for medical tests, where effectively, you know, you could say, oh, we need to do screening for cancer for everyone, so we pick them up earlier. But medical professionals say, yeah, but there's going to be so many false positives that we cannot do that, because then we're going to have to treat many, many healthy people. So that's not possible. Similarly, if you're trying to have a test in order to detect fraud or to detect terrorism or to detect any other thing, let's say you have a test that you apply to everybody who enters an airport, even something that has 99% or 99.9% accuracy will still have so many false positives that at the end of the day, you're still more likely to have an innocent person when you stop them. So that's a fundamental problem for any system that is trying to do detection in very, very large cohort, and that's something that that is usually difficult to grasp before you actually do the maths. So how can we touch that a little bit more? So there is an approach for explaining problems like this, which makes it much less likely to make poor judgment. That's what's called natural frequency explanations. So basically what they involve is imagining concrete populations of a fixed sample size. So for example, 10,000 people in a room, okay? And considering the proportion of population as counts, okay? So how many people in the room have the plague, okay? So we can use this to visualize the problem, and explain this apparent paradox. So that's what you have in this graph on the right. Okay? You have the whole population that is now simplified to effectively this graph of, I think there are 20 columns and 10 rows maybe, yeah. 20 columns and 10 rows, yes. So that's 200 little figures there. Okay, so we reduce the population to 200. And what we've done is labeling those people according to the problem that we have. So basically, all the people that are in black here are people who tested negative. Okay. Now what you have is the people in orange, whereas the people that have tested positive according to those numbers. And the person here that you have is the person who, with the black background, orange with the black background, is the person who actually has the plague and tested positive. So effectively, by reducing that to a smaller number, it's possible to visualize the reason why you have this counterintuitive result is because basically, even though it appears that 95% is quite accurate, the quantity of false positive is much larger than the prevalence of the disease. And there is, and this is just what's driving this. Okay, so the next notion that I want to introduce, now that we've seen Bayes rules, and you will be using Bayes rules in the lab if you've not started doing that already, basically you will be using Bayes rules in the labs in order to update your belief about where the submarine is every time you make a survey in one location. Okay, so this is how you're going to do it. So effectively you're going to have a prior distribution, and then you're going to regularly update your posterior according to that. That is what you're going to do. So another notion that's extremely useful, although it may not be obvious a priori why, is the notion of entropy. So that's a key property of a probability distribution, and intuitively that's a measure of the surprise that an observer would have when observing draws from the distribution. Okay? So if you draw samples from the distribution, or surprise is likely to be the observer. Okay. Or alternatively, this is the log measures of the number of distinct states that a distribution could represent. What does that mean? A flat uniform distribution, let's say that you have all of the possible outcomes and they all have exactly the same probability. This is a distribution that is very surprising because if you were to try to gamble on that, you don't know what's going to happen. There's no edge you can have. You don't know what is going to be the next thing. On the other hand, if you have a distribution that's very narrow and peaked, what that tells you is that one outcome is much more likely than the others, right? That's exactly what it tells you. So that means that you could make guesses. You just say, well, it's much more likely that this is going to happen rather than the rest. So in a sense, the outcome is less surprising for you. Okay. So basically, what entropy is a precise quantification. It gives the information that is embedded in a distribution. Okay. Now, the units of information normally, as computer scientists, you know, are bits. Okay, where one bit of information can use the answer for exactly one yes or no question. Okay, and for more information, gives you more. You need more bits. So the entropy, what the entropy does, it tells you exactly how many bits are needed at minimum to communicate a value from the distribution to an observer who knows the distribution already. So again, think of the extreme case. If you have a distribution where you have effectively one bin, one value that is with a probability of 1 and the other a probability of 0, you need 0 bit of information to convey that. There's only one possible outcome. If you had 2 possible outcomes, so 2 bins where you have equally likely thing, you would need 1 bit in order to provide that, okay? And so on and so forth. The more outcome you have, the more bits you need, okay? That's basically the idea. So alternatively, you can see the number of distinct states of the distribution described as being 2 to the power of the entropy of this distribution, and that is called the perplexity of the distribution, and it can be fractional. Now, in practice, how do you calculate that? So the entropy of a discrete distribution of a random variable x can be calculated as being the sum over all value of x of minus the probability of x multiplied by the logarithm in base 2 of the probability of x. Okay? So you multiply the probability with the logarithm of itself. So basically, that should remind you this formulation of something, because that's exactly the formulation of the expectation of a function we've seen before. So it's the expected value of the log probability of a random variable. Okay? So, or it can be seen as the average log probability. So why is it useful, and what can we do with that? Let's take an example. Let's say that you're tossing coins, okay? So this is sampling from a discrete random variable that can take two states, head or tail, two possible outcomes. If we call the two possible states 0 for heads and 1 for tails, then we can write that with single parameters where p of x is equal to 0 is equal to q, and so for heads, and p of x is equal to 1 for tails is equal to 1 minus q, because one of the two need to happen, okay? And q is effectively one parameter that tells you the probabilities. Now, what can we say? If this process is very biased, whoa, chair behind me. So if this process is very biased, and heads, for example, are much more likely than tails, then q is going to be much smaller than 0.5. And the observer will be unsurprised most of the time, because he knows that this coin is tricky and always gives heads, okay? If he has to bet, you will always bet on heads, because you know it's more likely. Now, if the process on the other end is unbiased, q would be equal to 0.5, both are equally likely, and the observer will have no way to predict whether head or tail is more likely. Now, for this distribution, we can write the entropy using the formula we've seen before. That is then the sum of the probability that x is equal to 0, so tail multiplied by the logarithm of this probability, plus the probability that x is equal to 1 multiplied by the logarithm of this probability. And if we plug in q in this equation, we end up with this formulation here that is exactly the same thing. Now we can then plot that, and that gives us effectively a representation of this entropy depending on how biased the coin is. And we can see that effectively we have this entropy that is very low for cases of a very biased coin, and that is increasing until it reaches a maximum when the coin is completely unbiased. So that corresponds to our intuition. An unbiased coin toss is the most surprising distribution, okay? Now, entropy is critically important concept in information theory. So when you try to effectively calculate or to communicate information and communication systems. But more importantly for this course, where entropy is useful is that we can measure how well Bayesian updating is going by measuring the drop in entropy of the posterior belief. So let's rewind that a little bit. I told you that the entropy was larger when the outcome is surprising and smaller when the outcome is unsurprising. Now, if we're having a whole program that is updating our posterior belief in something according to evidence, what we'd like is, as this process goes on, we become more and more certain about what is the outcome. Where is the submarine? Who is guilty? Okay? So that means that what we should see is that we should see the entropy going down as we go through our process. And this is why entropy is so useful, because if you have a probabilistic representation of what is your best guess of what is the output of your program, that means that measuring the entropy gives you an idea of how far you're going or better you're going after each iteration of your process. So that's, in this sense, why entropy is extremely useful in Bayesian updating, but in general, really in machine learning. So if we go back to the diagrams, we can also have a look at how we can apply that here. So we go back to a letter-based diagram example where we can calculate now the entropy of each conditional distribution P of Ci and Ci minus 1, which can tell us how surprised we will be by the character that might follow a character Ci. Okay. So we can see when we do this, that observing a Q means that the next character isn't surprising at all, because we know for sure there's going to be a U, because that is the only possibility in English language. Therefore, the entropy here is equal to 0 exactly. There's only one configuration in the world possible. Likewise, if we see a space character here, that gives us very little information, and the next character could be anything at all. The character after the space will surprise us. Although I've not included, actually I'm saying that, but I've rephrased, I've changed the graph and now I've removed the spaces, so that's not the case. But let's say if you have, another example is if you have, for example, a Y here, you have a very large entropy. So as a summary, as we've seen today, we can represent probabilities between random variables using joint, marginal, and conditional probabilities. Okay, so that's the way we combine this. Okay, Bayes rules. The big thing is that it allows us to invert conditional probabilities and to update our belief, the posterior, when new evidence is available. So this is a process we can do several times, and that is particularly suited to any computational process. And entropy is a tool that we have in order to model uncertainty and will be useful to effectively assess how effective the Bayesian update was at increasing our knowledge. Okay, and that's everything I had for today. So a bit early again today. What we'll do next week is that we're going to take everything that we've seen during the last 2 weeks, but we're going to look at what happens when instead of having a discrete distribution, we have a continuous distribution. So the concepts are going to be exactly the same, but the way we do the calculations will have to be more complicated in order to deal with discontinuity. Okay? And in the meanwhile, if you look at the lab, you'll see that you have the opportunity to apply what we've seen here on this problem of finding the submarine. Any question? No? Okay, then have a nice weekend, and I'll see you next week.
Free to see, but it's better to arrange a meeting if you want to chat or to send the question via Teams. Yeah, well, I was in the lab the whole morning. I was there for 4 hours. You come to the lab?
Yeah.
You should have come and talked to me.
My lab session was just an art.
Sorry?
My lab session was just an art, so I did my lab work.
Yeah, but it's a good time to come and talk to me. I'm always sitting there for 4 hours. No one is talking to me. So it's a good time to use for that, right? So what is your question? Do you want to, I mean, you can send me a message. If needed, then we can. Yeah, just send me a message. But I mean, some things we can just resolve either during the lab or just by.
这个应该是麦吧？那个什么声音的那个接收声音的。
But common resolve. Yes.
We want to ask the final exams will be use the paper and pen and paper, or on the safe exam.
There's going to be safe exam browser. So you're going to be in computer.
Yeah.
It's going to be Moodle. You're going to have boxes.
So we are going to the lab.
Yeah. It's going to be in the lab, but you're not going to have access to anything.
Okay, I know that. I know this kind of application, right? So we need to log into the safe exam, right?
Yeah, it'll be the safe exam browser. Yeah, that's it. Yeah.
Okay, I understand. Yeah.
And I mean, we've been doing that for a few years. It works.
Yeah,
in many ways.
Yeah. Thank you.
I mean, you'll get some more information from the lab. If you have a technical problem when you're there, just raise your hand and ask one of the invigilators. Okay?
Yeah,
we'll be able to help you. So,
So the lab exam will include kind of calculate and some.
Yeah, so I mean, you can look. The best is if you look at the last 2 years exam, you'll have a pretty good idea of what we're doing.
Okay, it's mostly similar, right?
Yeah, it's the most similar, and in terms of question, there's no big departure.
Yeah.
So we can ask you very simple calculations.
Okay, we understand.
And we can ask you to write pseudocode.
Okay.
or we can show you things, graphs.
So is there
like
any
that.
the answer on the Moodle like the last 2 years
I've
of
not
the
provided the answers.
you didn't provide.
Um,
So we just want to see the example of the answer. Maybe
I might. I'm not sure. But for now, I think if I do, I will provide them much later.
yeah
Because what I want for now is for everyone to try
to
and
finish
answer
with
the
themselves.
question themselves.
Yeah, we understand.
Because the problem is that what I found is, as a lecturer, is that people keep on asking for more questions, for more answers. You just
Yeah.
provide them. They just look at the question and answer. And then, oh, I
Yeah.
can do it.
Yeah.
Then they get to a new question where they don't have the answer and they can do it.
Yes.
So I think the point is what I want is to give you, you should be able to answer those questions. Just sitting down, looking at it, and possibly looking at the lecture.
So I also want to ask kind of the final marked answer. Like, should we just write down the calculate the progress in the in that on the or just write down the final
No,
answer?
you should always put your steps, your
There-
reasoning.
yeah.
Because
Okay.
the way those questions are marked is that you always have partial mark if you get something wrong.
Yeah.
So if your ID is correct but you made a mistake,
Yeah.
you're still
we're-
gonna get most of the marks.
Yeah.
We don't really care
Okay, we
about
got
it.
it. Yeah.
We don't really care whether you can do
Yes.
the calculations right. It's not
Yeah.
the point.
Okay. We
The
understand.
point is whether you're trying to do the right calculation.
So the most important is the step we do.
It's a step. You need to make sure that whoever is marking understand what you're trying to do.
Yeah. Thank you.
Because
Yeah, we understand.
sometimes you have questions, you have answers where you have no idea what it's
Yeah,
typed, so then it's difficult to define.
Yeah. Thank you. Thank you.
We're not trying to trick you. There's no trick in the exam.
Okay.
It is just about testing whether you understand the specific discussion.
Yeah. Thank you.
And so that's why. So if you can do last year's exam and let's say the year before, if you sit down just in exam conditions, sit down and you think you can do them,
Yeah. Yeah, we
then you'll
understand.
be fine.
Yeah. Okay. Okay. Thank you. Thank you.
யாரா இவன் தான் நான் எங்க ரெகுலர்
me.
Hello.
I might have an emergency in 20 minutes. I will stay
A
here.
planned emergency.
Yeah, because I don't. Yeah.
I don't need to know.
All
But
right.
yeah, if you need to go, that's fine.
Okay, so just watch as much as I can, and I will just
Yep,
go. So
I totally
I mean no
understand.
disrespect.
Yeah,
Okay.
yeah, no, I
All right.
totally understand. Thanks for letting me know.